Have you ever wondered about the secrets of the cosmos, about the grand design of our universe? An intriguing question that has captivated the minds of many throughout the ages, from the smallest subatomic particles to the vast expanses of interstellar space. Our universe is a rich tapestry of mysteries waiting to be unraveled. In our relentless pursuit of knowledge, we have come across intriguing concepts and phenomena, but the holy grail of physics remains elusive, a unified theory that could explain everything. This is the so-called theory of everything. It's a quest to decipher the cosmic code, to find a single, elegant equation that could weave together all known laws of physics, bridging the gap between the quantum world and the macro-universe. Today we explore two promising candidates for this theory of everything: string theory and loop quantum gravity. These theories, complex as they are intriguing, might hold the key to unlocking the universe's grand mystery. Scene script. Dive into the world of tiny, vibrating strings, the fundamental entities in string theory. Imagine a world where everything, you, me, the stars, and even the most distant galaxies, is made up of tiny, vibrating strings. This is the basic premise of string theory, a theory that seeks to harmonize the universe's largest and smallest forces. In this theory, the fundamental particles we know, like electrons and quarks, aren't point-like dots. Instead, they're tiny, one-dimensional strings. And these strings don't just sit there, they vibrate, each with its own frequency. And it's these vibrations that give particles their unique properties, like mass and charge. It's like each particle is playing its own little tune in the grand symphony of the universe. But string theory doesn't stop at the subatomic level. It reaches out, grappling with the very fabric of the universe itself. It predicts the existence of multiple dimensions, 10 to be precise, far beyond the three of space and one of time we're familiar with. Now you might be wondering, where are these extra dimensions hiding? Well, according to string theory, they're compactified or curled up at such minuscule scales that we can't perceive them. Yet they could give rise to the idea of parallel universes, a concept that has fired up the imaginations of scientists and science fiction writers alike. String theory also brings something unique to the table: the inclusion of gravity. This has been a sticking point for many other theories, but not for string theory. It naturally incorporates gravity, potentially bridging the gap between quantum mechanics and general relativity. However, it's not all rosy. String theory has its detractors. A major criticism is its lack of experimental evidence. Despite its mathematical beauty, we haven't yet been able to test it directly. This has led some to question whether it's a theory of physics or merely a mathematical construct. String theory, a theory as fascinating as it is controversial, might hold the key to understanding our universe. Let's shift gears and dive into the quantum loops of loop quantum gravity. This theory, often considered a strong contender in the hunt for a unified theory, takes a rather different approach to reconciling quantum mechanics and gravity. At its core, loop quantum gravity, or LQG for short, proposes that the fabric of spacetime is not smooth, as Einstein's relativity would have us believe, but rather it's made up of tiny, discrete loops. These loops are so minuscule they're about 100 million billion times smaller than a single atomic nucleus. This granularity of spacetime is a fundamental assertion of LQG, and it's this that gives the theory its name. One of the most profound implications of loop quantum gravity is the possibility of a finite universe. If spacetime is indeed composed of these tiny loops, then the universe might not be infinite after all, but rather quantized, like the energy levels of an atom. Loop quantum gravity also offers a potential theory of quantum gravity, something that has eluded physicists for decades. By treating gravity as a quantized entity, LQG provides a framework that is compatible with the principles of quantum mechanics, a strength that makes it a compelling candidate in the search for a unified theory. However, like all theories, loop quantum gravity has its weaknesses. One key challenge is the lack of a clear explanation of the nature of dark matter and dark energy, two mysterious entities that comprise roughly 95% of the universe. If LQG is to stake a claim as a theory of everything, it must find a way to account for these enigmatic components. Loop quantum gravity, a theory still in its infancy, could potentially revolutionize our understanding of the cosmos. As we continue to explore the quantum loops of the universe, we may find that the answers to some of our greatest questions lie not in the vast expanses of the cosmos, but in the tiniest loops of space-time. So we have two intriguing theories, each with its own strengths and weaknesses. On one hand, there's string theory. This theory suggests that the fundamental particles we observe are not zero-dimensional points, but one-dimensional strings. The vibrations of these strings give rise to the properties of the particles, like their mass and charge. It's a theory that beautifully marries the laws of the large, general relativity, and the laws of the small, quantum mechanics. On the other hand, loop quantum gravity proposes a different approach. It suggests that space and time themselves are quantized or broken up into discrete chunks. This theory avoids the mathematical inconsistencies that arise when we try to apply quantum mechanics to gravity. Both theories are bold attempts to solve the same problem, but from distinct angles. They offer tantalizing glimpses into the fundamental nature of the universe. Whether it's string theory, loop quantum gravity, or a yet undiscovered theory, the quest for a theory of everything continues. The universe, in all its wonder and complexity, still holds many secrets. The search for a unified theory, a theory of everything, is not just a quest to uncover these secrets. It's a journey that drives us forward, pushing the boundaries of our understanding and fueling scientific innovation. It's a narrative that encapsulates our collective yearning to make sense of the world around us and the universe beyond. Each theory, from string theory to loop quantum gravity, offers a different lens through which we can view and understand the cosmos. They challenge us, inspire us, and most importantly, they keep us questioning. They are the stepping stones in our continuous journey of discovery, a journey that is as vast and infinite as the universe itself. Our search for a unified theory is a testament to our resilience, our tenacity, and our unyielding curiosity. And so, the quest for a theory of everything continues, a testament to humanity's insatiable curiosity and desire to understand the cosmos.